Good afternoon. This is our Project 4 presentation for future DUV lithography. And if we go on to the next slide, I am Daniel, that's Alvin, that's Kevin, that's Ethan, that's Abara, and this is Ben. And this is going to be our Project 4 presentation, and we're going to leave it off with Kevin.
Previously, from our Project 3 research, we discovered the importance of DUV lithography for continuing Moore's law in the broader semiconductor industry in the 1990s and 2000s. With this knowledge, we researched deeper into how exactly DUV evolved from its early stages to its modern form. The transition from older G-line and I-line systems into DUV required major technological shifts, with the largest of these being the move from gas discharge lamps to excimer laser light sources. When gas discharge sources physically could not reach the shorter wavelengths needed for advanced chips, excimer lasers like KRF at 248 nanometer wavelengths and those based on ARF at 193 nanometers became the foundation of modern lithography. Excimer lasers function when dimers, or compounds with two of the same element bonded together, are chemically excited to release energy in the form of light. And as a result, while offering shorter wavelengths, excimer lasers also introduce much greater system complexity since they rely on high-pressure gas mixtures as well as extremely clean optical paths. Another major area of development during this era was vacuum technology, when the industry moved to immersion DUV, which we'll get into later, but it's basically placing water between the lens and the wafer. Vacuum companies had to redesign their systems. Companies like Edwards and Pfeiffer, which are the current world leaders, developed pumps that could maintain ultra-clean environments and rapidly handle corrosion, liquid handling, and also handled rapidly evolving resist chemistries. High vacuum performances were also playing a crucial role in keeping optical paths clean and minimizing particle contamination, both of which are critical for high NA imaging. Their adaptability allowed immersion lithography to become practical and reliable. And finally, DUV lithography also depends on extremely complex global supply chains. ASML currently is the leader in assembling the world's advanced scanners, which is just another word for lithography machine, but they rely on specialized partners for key subsystems. For example, Zeiss provides high-precision optics with each DUV lens costing millions of dollars and requiring sub-nanometer surface qualities, while other companies like VDL, ETG, manufactures precise mechanical assemblies, and companies like Neeways supply embedded control electronics, while MKS Instruments provides gas, vacuum, and photonics supplies. All of these companies are working in tightly connected ecosystems with even minor delays like a lens imperfection or a pump shortage impacting the entire supply chain. This interconnectedness is one reason why DUV lithography remains not only technologically complex, but also economically and logistically significant in today's chip industry. And next, I'm going to pass it on to Albara for performance and characteristics, which is defining what a good DUV performance actually means.
Thank you, Kevin. The most important metric is resolution, which is essentially how small a feature size is able to be printed onto the wafer, and that is constrained by numerical aperture and the wavelength size. As the numerical aperture increases, the wavelength decreases, resolution also increases, and it has been scaled down from 250 nanometers to 38 nanometers. The numerical aperture also has been scaled, obviously, from 0.45 to 135, from dry to immersion, which utilizes ultra-pure water between the wafer and the lens itself, and that has increased the resolution, as mentioned before. The wavelength obviously has been scaled to a smaller wavelength from 248 nanometers to 193 nanometers from krypton fluoride to argon fluoride. And DUV lithography early on used to produce 80 wafers per hour at a much lower resolution to 300 wafers per hour, a much higher resolution. Over the 3 decades of DUV lithography history, it's been constantly improving with the critical dimension nearing 38 nanometers. Critical dimension is essentially how small is the smallest feature size, and it's about half a pitch size. The printable pitch size is around 76 nanometers, which is, and a pitch is essentially the center to center distance between two feature sizes. And the overlay accuracy is how accurate a lithography machine is able to place a layer on top of another, and it must be within 1 nanometer for the wafer itself and the chip itself to function. and produce a much higher yield rate. The critical dimension uniformity is essentially how consistent each wafer, each feature size and each feature is within the wafer throughout and the chip itself. So with a much lower critical dimension uniformity, it produces much higher yield rate. And as mentioned before, DUV lithography, while maintaining all these metrics, must produce 300 wafers per hour. Immersion interface has increased numerical aperture, which replaced the dry space between the lens and the wafer with ultra pure water, which has increased the refraction index of the optical lens to absorb light, which has increased the resolution size. Abbreviation corrected optics and dual stage mechanics helped increase the yield rate and the accuracy of the DUV lithography, and high powered lasers and height mapping increase the dual stage accuracy, as it also utilizes exposure and measures at the same time. Moving on to Daniel with the rest of the metrics.
Thank you, Abara. Now with self-alignment, double patterning, and quadruple patterning, this allows for the printing features to surpass the optical limit of the DUV lithography machine. The resist chemistry reduced stochastics that allows for the photons to be increased or more concentrated onto the wafer. As you can see in the image, the wafer, without using this technique, has decreased area onto the wafer, while as when using the chemistry, the images imprinted on the wafer are increased and in the area, which will reduce how much of the wafer is being used. And the process window, that just allows how accurate the image from the photomask is imprinted onto the wafer. Now if you go on to the next slide, without using the previous techniques covered on the previous slide, the numerical aperture can only go up to 1.35. Most potential lens materials strongly absorb 193 nanometers, blocking further NA growth. For the depth of focus collapsing rapidly, as CD shrinks, the acceptable focus range becomes extremely small. For those stochastic variation dominating failures, random photon and resisting reactions cause unpredictable pattern failures. And for optical resolution fundamentally saturated, even with computational tricks, 193 nanometers optics cannot scale much further.
All right, thank you, Daniel. I'll be talking about some technical challenges that DUV has faced in the past. So one challenge is that the microcomponents of the resist layer will leach into the water, contaminating it. And so one solution to this is to add a top coat layer on top of the resist layer made of hydrophobic polymers. However, a better solution is to incorporate these polymers directly into the resist layer, removing 2 steps to the process, which would be adding the top coat and removing it. Another challenge that DUV has faced is that bubbles in the water can refract the light, and the solution to this is an optimized nozzle shape that ensures laminar flow to keep the image clear and uniform. Another challenge that DUV has faced is that water can transport contaminants onto the wafer, causing defects, and the solution to this is the water confinement method, which reduces the amount of wetting and drying events. And finally, another challenge is that sometimes there's just water left on the wafer, and to fix this, researchers developed a gas seal system that utilizes air knives to brush the water off of the wafer. Now I'm going to pass it to Ben with some current challenges.
Thank you, Ethan. The main challenge that DUV currently faces is that it reaches optical limit of about 38 nanometers using immersion single patterning. And you can get lower node sizes using things such as double and quadruple patterning, but that increases both the cost and the complexity. And then you have to balance whether or not you want to do hybrid DUV lithography, just EUV, or simply DUV at a higher cost and complexity. Next slide. Okay. However, DUV still has its benefits. As I said, you can use techniques to get smaller nodes, such as immersion and double and quadruple patterning, and it's much more cost effective than EUV lithography, as one DUV machine maybe costs $20 to $50 million, and an EUV machine can cost upwards of $150 million with infrastructure not included. And it's also less complex than EUV lithography, which means you can output a lot more volume. And as you can see here, the market share of DUV projects to stay relatively similar to EUV lithography. Some future barriers of DUV lithography is that they all really revolve around that it's at or approaching its optical limit. And in the future, it's going to be more and more dependent on double and quadruple patterning, which is not good because it's more costly and complex than single patterning. And as EUV improves and gets cheaper, then DUV might become more obsolete. Another future barrier is stochastic defects as the node size gets smaller. A stochastic defect is a random or uncontrollable event that's just based on the statistics of the photon particles. They're mainly caused by photon shot noise, which, as you can see here, increases the lower nanometers you go down. It's inverse proportional to node size. And basically it's where an uneven amount of photons hit each area, causing slight defects in the nodes. And multi-patterning can stop this because if you pattern over it multiple times, then it will even out the statistical errors. And photoresist optimization is also being developed, which enhances the sensitivity, which will decrease stochastic defects. And on to Ethan.
All right, thank you, Ben. So Zeiss is a tier 1 supplier for ASML's optical systems, including lenses, mirrors, and windows. Zeiss first supplied ASML with an optical system in 1983, and the two companies have been strategic partners since 1997. ASML requires lenses with extreme uniformity and smoothness, and has trusted in Zeiss to provide these for decades. Since Zeiss is ASML's only main provider for optical systems, even one defect in one lens can cause months of delay, disrupting downstream fabrication. To get these lenses so uniform, Zeiss uses calcium fluoride crystals. Because calcium fluoride has such a low defect density and its crystal ingots take about a year to grow, it makes up about 50% of the total material cost for DUV optical systems. Next. Some other materials that DUV requires are known as the conflict minerals, which include tin, tantalum, gold, and tungsten. These are denoted conflict minerals since they are typically found in regions of instability near the Democratic Republic of the Congo. ASML takes some precautions on the supply chain for these minerals. For example, they require a reasonable country of interest inquiry, which identifies the countries of origin of the minerals used for ASML's products. ASML also conducts third-party audits of the mines and smelters from which these minerals are from. ASML looks to buy minerals that were smelted by RMAP, which is Responsible Minerals Assurance Process Validated Smelters. And now on to Alvin to conclude.
Thank you, Ethan. So I'm going to talk about the future of the DUV lithography, which is about testing relevance and market growth. The first thing is about the DUV. DUV is still a foundation for a major node and hybrid node, which powers a artificial intelligence, auto industry, and edge computing. Also, this DUV also reaches EUV cost gas, which one EUV can cost $150 million, and DUV market is almost hitting a 23.69 billion by 2031 with 6.4% compound annual growth rate. The next is about the tech limit breakers that we talked about in Project 3 and Arbora. Artificial intelligence is helping a inversely direct technology which costs defect by 50%. So self-line quote-unquote patterning enables 5 nanometer in equivalent in China. China has those facilities. The low resistant energy can save 18% with same performance that we're not saving, which reduce the carbon footprint overall. The next is about the diversify from Asia market, Asia risks, which US and EU OPEC ramp up. ASML is trying to produce 56 low NA EUV machines to US and 10 high NA EUV machines to US, which is gonna be bridges 2 nanometer with EUV machines. And SMBE is also trying to make a 28 nanometer machine, which is going to be a pressure the prices, prices goes down. The next one is about the broader ecosystem role. So there is a, so DUV is still a backbone of the so DUV is still a backbone which was, so DUV was a bridge before and now it's becoming a backbone of the industry since we need the DUV a lot because of the cost. It's also a edge computer powerhouse. And we are moving TFAB integration, which is going to be also a hybrid with DUV and EUV, and demonstrate a advanced nodes and sustainable equitable focus. The closing business should be innovation ensure viability, global tech equity boost, DUV scale inclusively, and embrace hybrid now. These are our reference. Thank you for watching. If you have questions, just comment down on the comment section. There you go. I think